So today I'm going to do your 15.2 notes. Tomorrow, which is Thursday, you will have both homeworks number 8 and 9 due. I will put up the 3.5 key, and then I'll also put up the chapter 15. I think there's one of the answer keys missing, so I'll do that at the same time that this video is posted. So to start off, you're going to take out your notes for 15.2, and you're just going to follow along as if we were in class. So 20% of cereal boxes have a surprise toy in them. You get excited and purchase 3 boxes of cereal. So 20% as a probability. So the probability of having a prize, let's do just a surprise, the probability of S is equal to 0.2. So here's box 1, here's box 2, and then here's box 3. So box 1, either you have a prize or you don't have a prize, so that we'll use an N. And then given box 1, you could get box 2, which has a surprise or doesn't have a surprise. And then box 2, surprise, not surprise. And then box 3, surprise, not surprise, surprise, not surprise, and so on. And then remember, to make this a probability tree, we actually have to write the probabilities on there. So a surprise is 0.2, and then not a surprise is 0.8. So here's your 0.2, here's 0.8. Alright, and at the end here, I'm going to write the probabilities, but I'm actually not going to find the values. I'm just going to write them the way that they're showing up, and I may simplify them, just so I see them a little bit differently. So the first one is 0.2 times 0.2 times 0.2, which would be 0.2 to the 3rd power. The second one looks like it's 0.2. There's now, so I'm here, 0.2, 0.2, and then 0.8. So I have 2 0.2s, but I only have 1.8. The next one I have 2 0.2s, oopsie, wrong way, my bad, and 1.8 in the middle. The next one, it looks like I have 1.2, but then 2.8s. Next one, it looks like I have, let's hope I'm doing this correctly, NSS, so 2 0.2s, 1.8, 1.2, 2.8s, and N, so that's 0.2, and then 2.8s, and then this should be 3.8s, and then I'm just going to double check them because I'm afraid I might have messed up somewhere. So S and S, S and N, that's 2 N's, NSS 2 S's, NSN 2 N's, NNS 2 N's, and NNN. Alright, so those are all the probabilities. Now I haven't multiplied them out. I actually wanted you to take a look at them. The way they're written, they kind of look similar to when we were doing binomial, and we are going to use this concept. So here's just the tree diagram, and what I want you to notice is if I asked you, what is the probability of getting all 3 surprises? So give me 1 second. So all I did was make it a little smaller so I had some room. So this here would be 3 S's. This one would be 2 S's, 1 N. This would be 2 S's. This would be 1 S. 2 S's, 1 S, 1 S, and then 0 S's. So what's interesting is I started by writing the ends, but in reality, if I know how many surprises I get, I also know how many I didn't get. So I'm just going to start out like that. Now, if I want to write probabilities and do the probability distribution, which is here, I'm going to take this and copy it over actually underneath so that we see the values. So if I want to do a probability distribution based on the number of prizes, then over here, this would be the probability that, so X is equal to the number of prizes that I actually received, the surprises or whatever they called it. So if I wanted the probability that X is equal to 0 prizes, which is how this would be written, this one would be written as the probability that X is equal to exactly 1 prize. This is the probability that X is equal to 2 prizes. And then this is the probability that X is equal to 3 prizes. So, in orange here, let's go through. I want no prizes at all. That's this last one right here. And I'm checking them off because I just want to make sure that my distribution has all of them. Then that probability would be 0.8 to the 3rd power. Now, one of them I have, here's 1, 2, and then 3. And notice they look exactly the same. There's 3 of them, though. So I'm just going to write them as 3 of the 0.8s with 1 prize. Sorry, wrong way. 0.2 with 1 prize, but then the 0.8, I think there were 2. And then the next one is if I had 2 prizes, and it looks like that's this one here, and this one here. So 2 prizes. There were 3 of those. So 0.2 happened twice, but the 0.8 only happened once. And then all 3 prizes, that looks like it would be the one that's left over, which would be this guy right here. So I think we got them all. And that would be 0.2 to the 3rd. Now I'm going to move things around a little bit, line things up a little bit better. So the first one, there's no prizes, which means that there were 3 not prizes. And then down here, I'm going to add in a 0 for if there were 3 prizes, then there had to be 3 not prizes. And I'm even going to add in the coefficients of it happening once, because in my probability tree, it only happened once. What you should notice, that looks very similar to the distribution of A plus B cubed. So the binomial theorem, when we did that, we did A plus B cubed, and we were able to write out each of the terms. And what you'll see here is that each of the terms aligns to a probability. If I was to use my calculator, find these exact probabilities, because it is a distribution, this is all the possible ways I could get prizes, and these probabilities added up would equal 1. And other things is there's no way for me to have 0 prizes and 1 prize at the same exact time. These are all exclusive of each other. All right, so that was the distribution. So a binomial experiment is actually what you're looking at here, and there's going to be 5 properties. The first property is the fact that you have N is the number of trials, and all your trials are identical. So what does that mean? It means in the serial, a trial was picking a cereal box. So we had 3 trials, meaning I chose 3 cereal boxes. When I say that they were identical, every single time I chose, the probabilities of getting a prize and probability of not getting a prize never changed. An example of something that would not be a binomial experiment, but could kind of look like one, marbles. If you don't replace them, the first marble you pick versus the second marble you pick without replacement, that second marble's probabilities change, so it's no longer identical trials. The second one, each trial has 2 outcomes. Exactly 2 outcomes. P is whatever we want. and Q is not what we want. And what you'll notice is that because they only have two possibilities, we call one of them a success and one of them a failure. The probability of success plus failure has to equal 1, because if there's only two outcomes, then those two probabilities have to add up exactly to 1. So in our serial, the success was getting a prize that was 0.2, and our failure was 0.8, which was not getting a prize, and they added up to 1. All right, third property is the fact that exactly what I just said, success probability plus failure probability equals 1, or obviously the not failure property is equal to 1 minus p, things that we should know. The fourth is that all the trials are independent, so one trial doesn't affect another trial. So replacing marbles, when you're looking at replacing marbles, you can actually turn that into binomial. When you don't replace a marble, because the second marble, taking it out depended on whatever the first marble was, it's no longer independent. Remember that mutually exclusive and independent are not the same thing. And 5, so we are always interested in the probability of X. We want to know the success for n trials. And this is a discrete probability, meaning you're going to be asked for things probability. You're going to be asked for probabilities of 0, 1, 2, 3, 4, and so on, up to the number of trials. Okay? So you can't have 1.5. All right. So, a binomial distribution. So how do we find an actual binomial distribution? It's going to look very, very similar. So things that you want to identify right away. When you do your binomial, you want to identify what your n is, your p, which is the probability of success, and then q, which is the probability of failure. And once you have that, you pretty much have everything you need. So, binomial distribution is going to look like, if I want to find the probability that x is equal to some number, how many successes I want, that will be equal to n, choose the number of successes I want, times p to the number of successes, times q to the n minus number of successes, which would be the number of failures. That should look exactly like the binomial distribution. A lot of times you'll see notation where we'll talk about the probability. Binomials, sometimes we'll do that x is a binomial distribution of n trials, comma, p being the probability of a success. So that notation you may see. That's how they will denote binomial. Binomial is interesting. They won't tell you that it's a binomial distribution. You will have to figure it out. How would you figure it out? You go back to the fact that there's only two possibilities, either success or a failure. All right, so actually before we get to this example, I want to go back. Yeah, I do want to go back. Underneath here, I want to show you how a marble problem could be made into a binomial, even though it may not seem as though it is. So, over here, you have a bag of marbles. There are 5 red, 6 green, and is that 11? So 9 blue. Find the probability of you choosing exactly 3 greens. So what did I just create? I created a binomial. A binomial where I would first have to tell you how many marbles am I picking. So of the, let's say, there are 20 marbles, but I am going to do a number of 3 marbles chosen. And actually, let's stay away from 3 because we just did one with 3. Let's do 8. Out of the 8 marbles, I now want to know the probability that I have 3 green marbles. So what does that tell me? It tells me that the probability of my success would have been the 6 over 20. The probability of a failure, which would be the reds are a failure and the blues are a failure, and that's 14 over 20. The only way this is binomial is if I mention that this is with replacement. As long as I replace that bag of marbles always has the same amount of marbles each trial. Now, if I do without replacement, then that is never binomial. People get really confused because there's 3 marble choices, but it's now a binomial. It's because as long as I ask you for exactly only one color, then I've turned it into one color versus the other color. So a success and a failure. If I wanted to ask you about 2 reds and 1 green, or 4 blues and a green, then that changes the problem. It can't be binomial because now I'm asking about more than just winning a color and not winning a color. Alright, so this example, Mr. Ish used to work in a pineapple canning factory, which is actually a true statement. He no longer enjoys canned pineapples. The probability of finding bug parts in a can was 0.012. Now that is a made-up number, but that was Mr. Ish's job, which is kind of interesting. He used to sit in a factory and look with a microscope at the number of bug parts in a can of pineapples, and if there were too many bug parts, they had to throw that can of pineapples out. And you could ask him how many parts he was allowed to find to let it pass inspection, because yes, there were bug parts that were allowed to be in the cans. So, if Mr. Ish checked 100 cans in his first hour of work, what is the probability of that? So, let's double check. Number 1, oopsie, there is an N. He's checking 100 cans. Each can is an independent trial. The probability of there being bug parts is 0.012. Therefore, the probability of not having bug parts, 0.988. Alright, so we have our values. It is a binomial distribution because either he finds a bug part or he doesn't find the bug parts. So, we're going to start out by always writing what exactly we want. So, in part A, actually, let me give myself a little bit more space. So, this is going to be interesting. Let's see. Let's do it this way. Okay, so only 4 cans had bug parts. So, the probability that X is exactly 4. So, that would be equal to, and we do write an X equals statement inside. So, that would be equal to 100, choose 4, 0.012 to the 4th power, 0.988 to the 96th power. And I'll be very honest, these are mostly going to be calculator problems, so you will be able to put this directly into the calculator. So here is my calculator. Let me see if I can make it a little bit larger. I think you'll be able to see it. So, first thing I want to write is N choose. So here's math, move over to probability, and you're going to go to number 3, which is N choose R. Depending on the type of calculator you have, it may look different than mine. My N is 100. My choose value is 4. And then from there, I can actually multiply it by 0.012 to the fourth power. And then I can multiply that by 0.9. Oh, Lord. So the calculator just froze on me, but mostly I wanted to just make sure you knew where NCR was. That's math. Move over to probability. And then it's the one that says N choose R. All right. So I won't be able to show you the calculator steps. I'm hoping that the calculator will start working in a little bit because I do want to show you some other things. All right. So next piece is all the cans had bug parts. So that's the probability that X is equal to 100. So every single can had bug parts. Well, that would be 100. Choose 100, which we know is a value of 1. So I'm not going to even worry about that piece. And then 0.012 to 100 power. And then 0.988 to the 0 power. Anything to the 0 power is also 1. So my actual value would be 0.012 to the 100th power. That probably will be a value very, very close to 0. So your calculator may just have 0.000, a bunch of zeros. At least one can had bug parts. So that would be the probability at least one. So of 1, 2, 3, all the way up to 100. So looking at that list, you'll notice that that is the same as probability of all of them. Subtract away the one and only probability not listed is the probability of none. So you will have to look at that sometimes and see, well, if they want us to add up way too many probabilities, that's probably not what they want. Instead, we're going to do a complement. So that would be 1 minus 100, choose 0, which we also know is 1, 0.012. I want no cans with bug parts. Let's see. And therefore, all the other cans have to have the bug parts. So that would be what I would put into the calculator to get my answer. All right? Using the calculator, so we know how to do the NCR. That's math. Move over to probability. And I believe it's number 3 or 4. Can't remember off the top of my head right now. But you will actually be able to use something else. Let's see if it's still frozen. Yeah. Oh, Lord. So there are 2 other buttons where as long as you write down what you would have calculated, you're welcome to use the calculator to do the physical calculation. So what I mean by that is when you are doing the probability of X equaling, and we'll use, to be honest, we're going to use a little X. You'll see that notation get used a lot. So whatever that little X is would be how many successes I have, and that would be the number of trials, number of successes, P to that power, Q to the N minus X power. And as long as you write that statement down, you are welcome to then use the calculator. There is binom PDF. So binom PDF, I was hoping to show it to you, but my calculator is still acting up. So where it is located, I can't remember off the top of my head, but I believe it's probably inside statistics. Let's see. I actually did pull up a command thing, but that also doesn't tell you where it is. I'm sure you guys can be resourceful and find the button. Just play around. It might be under list. It might be under math, ops. So binomial PDF, and actually it looks like I might run out of space here, so let me move it over a little bit. Binom PDF will find the probability of an exact amount of successes. So you will put inside the command how many trials, the probability of getting a success, and then whatever the number of successes are. And then press enter. It'll actually just give you the value. Now, there is one other calculator function. You'll find binom CDF, and this is a cumulative. And the command looks almost exactly the same. Number of trials, probability of a success, number of successes. Okay? What it finds for you is a little bit different. It finds the probability that the number of successes is less than or equal to that number x. So if I wanted the probability of having at most 3 successes, then I would use the cumulative. So the binom CDF. So these two things put together can pretty much find any binomial probability. It's understanding what you're using. And remember the complement, we may sometimes have to use complements. 1 minus the probability of what we don't want. That is going to be a useful thing for summing. So if you look at what's given here, you want to be really careful, because if I ask you for the probability of more than, so a greater than or equal to, I'm going to leave that on you to kind of figure out how to make it work using binomial PDF or CDF. And that should be everything. So, just a little summary. Remember, n is the number of trials. P is the probability of success. X is the number of successes. P of x, which we actually write as px equals, and that number, we'll do a little x, is the probability of x successes. Expected value. The formulas that you get for this section are, so in the middle of the board right here, so binomial distribution 5.8. Here is that notation I showed you, is how we denote that you are doing a binomial distribution. They actually give you the formula for a binomial distribution. 1 minus p is the same thing as q. They'll give you the expected value, which is the same thing as the mean, n times p. And then the variance is np, and this right here is actually the q. So they're giving it to you using a formula for q. So let me take a second, and I actually do want to copy that over. So remember that this is what you'll be given, and this here is just q, and this here is just q. So the expected value, which is the same as the mean, you'll just do the number of trials multiplied by the probability of a success. The variance then is the number of trials multiplied probability of success multiplied by the probability of a failure, and then the standard deviation is the square root of variance, which is MPQ. Remember that Q is equal to 1 minus P, and that's why they're trying to give you the formula without the Q. It gives you one less variable to memorize, okay? Or parameter. All right, so last piece, you're more than welcome to skip this part if you feel comfortable with it. Among the studies carried out to examine the effectiveness of advertising methods, a study reported that 4 out of 10 web servers remember advertisement banners after they have seen them. All right, so just from that statement, now I know that the probability of memorizing an advertisement is 4 out of 10, so I'm just going to do that as 0.4. Let's see. Letter A, if 20 web surfers, which would be, are chosen at random, so that's my n. What is the expected number of surfers that would remember the ad? So E of x would be n times p, and that would be 20 times 0.4. I'm not going to worry about calculating exact values here. Part B, what is the chance that 5 of those 20 will remember the add? So that would be the probability that x is exactly 5. And that would be 20, choose 5 times 0.4 to the 5th power, 0.6 to the 15th power. Part C. What is the probability that at most one surfer would remember? At most. So that would be the probability that you have no surfers remembering plus the probability that you have one surfer remembering. And so that would look like probability of 0. So that would be 20 choose 0, 0.4 to the 0, 0.6 to the 20. And then the other one I'll do in purple, plus the probability of 1 would be 20, choose 1, 0.4, 1, and then 0.6, 19. And then part D, which I'll have to squeeze up here. What is the chance that at least 2? At least 2. So that would be the probability. At least 2 would be 2, comma, 3, comma, all the way up to 20. So I'm going to do this one as a complement. And I would do 1 minus the probability of x equaling 0 and 1. Notation-wise, that's probably not the best notation, but I'm running out of space. We found that in part C. Therefore, you're just doing 1 minus part C's answer. So that's just a nice summary of a binomial distribution. So you should be good to do your problems. All right.